a few webinar logistics. I'm Andrea Silvestri, and again, welcome. So today's webinar is on the Honeycomb Solar Thermal Collector. And you can find the one-page infographic, 4-page findings, and the full report for which the webinar is based on at gsa.gov/GPG. Today's webinar is one in a series. Our next webinar in June will be on variable refrigerant flow. And this is an early GPG assessment of the technology. At the time of the original evaluation in 2012, GSA did not have any full implementations, so the researchers concentrated on recommendations on where best to deploy the technology. Since then, GSA has completed multiple VRF implementations, and June's webinar will present the results from the Pacific Northwest National Laboratories report, along with on-the-ground feedback from several GSA implementations of VRF. July's webinar will present results from a soon-to-be-released assessment of LED fixtures with integrated advanced controls. We'll be taking a break in August and then return in September with a webinar on a recently released report on high-performing commercial rooftop units. This report evaluated the first advanced RTU to meet DOE's high-performance RTU challenge. And that report, as well as the infographic and findings, are now available on the website. All GPG webinars offer continuing education learning units through the American Institute of Architects. To receive credit, you should receive a post-webinar survey, and by completing that survey, you can request credit. If you don't receive that survey, please contact Michael Hobson. During today's webinar, the broadcast will be set to listen only, and you can submit questions here in the chat box on the right side of your screen. And you don't need to wait to submit questions until the Q&A session at the end. In fact, we encourage you to submit questions well in advance of the Q&A session. Michael Hobson, a project manager with Emerging Technologies, will be facilitating today's webinar. And,
thank you, Andrea.
Over to you. Thank you.
Hello, everyone, and welcome. Next slide, please. So in today's webinar, Kevin Powell will be giving us a brief overview of GSA's Proving Ground program. After this overview, Jesse Dean from the Department of Energy's National Renewable Energy Laboratory and Greg Barker from the Mountain Energy Partnership will share details and results from our demonstration on Honeycomb's solar thermal collectors. Jesse and Greg's presentation will be followed by feedback from Marty Novini from GSA's Northwest Region 10 and also from Alan Miller from GSA's Great Lakes Region 5. Both were regional project managers for this study. Finally, we will end the webinar with an interactive Q&A session. And with that, Kevin, take it away.
Thank you, Michael. And next slide. Just a couple of things here. The first thing is that GSA, as well as the government at large, I think you've heard this probably in the media, is really committed to innovation. I think everyone recognizes that the way to do more with less, which is what we're being told to do, is to do that by doing it better and in our particular case, with technologies that can deliver better performance. There's two halves to our program, our Emerging Technologies program. There's the Proving Ground side, which is looking to validate next generation technologies. And then there's the pilot to portfolio side, which is looking to deploy those that make the most sense, have the biggest, quote, bang for the buck across our agency. Now, this particular webinar, I think, is going to be of some interest for a couple of reasons. First, there remains from, I think everybody has seen there's a new executive order that relates to the performance of federal buildings, and it commits or reestablishes the commitment to previous legislation that, in this area. And of course, in ESA, 2007, there is a requirement that federal buildings achieve at least 30% of their hot water demand, at least in new and renovated buildings, from solar hot water heating, if life cycle cost effective. Now, if the life cycle cost effective has been the rub, and particularly the rub in an environment where we have essentially we're the Saudi Arabia of natural gas. But with that said, I think we have a pretty interesting evaluation of a pretty effective solar hot water technology, not without its trials and tribulations in terms of real-world deployment, as you'll hear. So with that, let me turn this back over to the researchers that led this work, Jesse Dean and Greg Barker.
Hey, good morning, everyone. This is Jesse Dean with NREL. So I currently manage the support that NREL provides for the GSA Green Proving Ground. Do you want me to introduce Greg, or Greg, do you want to introduce yourself?
Sure. This is Greg Barker. Sorry. Yep, this is Greg Barker. I'm a contractor and do a lot of consulting for NREL and did much of the technical work for this project.
Okay. Okay, next slide. So we're going to spend about 15 minutes today and cover the results from the Honeycomb solar thermal evaluation. So my colleague Caleb was the technical point of contact on this and was in the process of leaving NREL when we were writing the report. So I'm going to kind of go through and present the findings, but Greg Barker was in charge of kind of all of the measurement and verification and all the modeling work. So if we have any questions when we get to the end, Greg can kind of help us on some of those technical questions. Okay, next slide. Yeah, so I think as Kevin mentioned, the impetus for this really comes from a ESA 2007 requirement. And I think it's important to remember that, you know, the statewide renewable portfolio standards were just getting started in kind of the 2004 and 2005 timeframe. And so in 2006, when ESA was being drafted, there was very few renewable energy deployments in the federal government. And so this was essentially a requirement that was trying to push federal agencies to include some level of renewables in new construction and major renovations. But as you can see in the second bullet point there, the renewable energy market, I think, has changed kind of dramatically in the United States since 2005. For example, you know, the cost of photovoltaic systems has dropped by 80 to 90%. We've also seen kind of a huge boom in natural gas production. And so we have, you know, natural gas prices that are 48% lower than they were when this was enacted. So, you know, instead of the normal trend of, you know, energy prices going up, we've actually seen, you know, natural gas prices go down for a number of years. And then just really quickly on the sources, you know, domestic hot water energy is primarily driven by natural gas heating and commercial installations, with about 23% coming from electric. So I think one of the main focus areas for this report was a combination of looking at, you know, where is solar hot water cost effective for GSA, and then how do these new and innovative technologies kind of fit into the market portfolio. Okay, next slide. So just really quickly on how solar works, this is just a graphic of a typical kind of closed loop solar system. And you'll see, you know, for example, they have a certain number of solar hot water panels that are ran in series, and then a certain number that are ran in parallel. And essentially, you know, based on the collector that's used and based on the design, you're targeting a specific kind of delivered water temperature and kind of BTUs of heat. For this specific system, there's a heat exchanger that separates the propylene glycol loop from the building domestic hot water. And so, for example, you'll see a controller in here that is typically set to turn on the circulator pump when the panel temperature is 20 degrees hotter than the tank temperature. But this is kind of just a standard solar hot water system. As we go through today, though, you'll see that we tested basically one system that is similar to this, and then one system that's what's called a domestic hot water recirculation loop system, and we'll go through the details of those. Okay, next slide. So the technology that was tested is a Honeycomb solar thermal system, and I think the best way to think about this at a very high level is the rate of heat loss from a solar thermal collector panel is the primary driver for efficiency. And so for this particular product, the innovation here comes in, designing a solar thermal system that reduces the heat loss. And so there's a transparent layer of this honeycomb insulation that sits above the energy collecting surface and allows for the panel to have a greater efficiency. And so we'll kind of walk through some of the specifics of that and what are good applications and what that means. But at a high level, this is essentially kind of a higher efficiency flat plate collector. Okay, next slide. So the demonstration was conducted at two different facilities. The first one is the Bean Federal Center in Indianapolis. The second one is in Auburn, Washington. And so this gave GSA kind of a nice use case for two different climate zones. You can see for the Bean Center, it essentially has kind of cold winters and hot summers with what would be considered kind of an average solar resource. And then the Auburn facility has mild winters and summers and kind of a low solar resource in Washington. On the graphic on the left, you'll see this is an 8-panel solar hot water system. They have 4 panels ran in series and then 2 sets of those, so 8 panels total. Just a standard closed loop system with normal controls and everything like the other one we discussed. The GSA regional headquarters building is a little bit different in that the domestic hot water that's heated actually comes from the domestic hot water recirculation loop. So for a lot of kind of larger federal buildings, they will have these domestic hot water recirculation loops that ensures that the faucets have hot water. And so essentially the solar hot water panels for this building tap into that domestic hot water recirculation loop and heat that water before it is returned back to the main system. It's a different type of design where, the entering water temperature into the solar hot water panels is normally around 110 to 120 degrees Fahrenheit. So it's a higher water temperature application. And that's kind of one advantage of this Honeycomb solar thermal system is, normally you would have to use an evacuated tube or another type of collector that's able to operate efficiently with higher inlet temperatures. So kind of a cool application in the two different types of designs you would normally see in GSA buildings. Okay, next slide. So this is a graphic of the system design, and then it also shows kind of the measurement and verification points. So I'll start on the Bean Center, and I'm not going to go, into tons of detail on exactly, each measurement point, but again, it's a more traditional system with solar collectors, a preheat tank, and then an auxiliary domestic hot water tank. So for the Bean Center, we were able to install the NREL instrumentation, and so we have, immersed thermistors and immersed flow meters, and outside air temperature sensors and plane of array pyranometers. So this is kind of a full instrumentation that allowed us to characterize, the energy usage of the domestic hot water system, the performance of the solar collectors and the system in general. As you can see, the system on the right is a lot simpler in that it's connecting to that domestic hot water recirculation loop. In this case, they did put in a storage tank, and the measurement and verification for this one was actually field installed by the vendor, and so NREL did not put in the measurement points on this. I think we did install a few additional sensors for like the pyranometer and a few other things, but you'll kind of see that some of the results aren't as accurate for the Auburn Regional Headquarters building. Okay, next slide. So the performance objectives for this project, the first one was, this is kind of a normal procedure within GSA of just looking at, does the performance match the manufacturer's claims? And so we were looking at, making sure that the performance of the collector was within 10% of their claims. And then we also looked at the efficiency of this versus flat plate collectors, and then this versus evacuated tube collectors. We looked at, did the overprotection work as expected? And I think that kind of gets into some interesting design considerations that need to be made as you're looking at these things. And then one of the main outcomes of the study was basically a modeling effort where we did a lot of modeling to look at, which loads and climate zones and installed costs solar hot water is cost effective and they can meet those ESA requirements. Okay, next slide. So this is the first performance objective of just making sure that the performance of the collector is in line with what the manufacturer has stated. And again, over on the left-hand side, you'll see that the gray dots have very good alignment with the yellow dots. This was the instrumentation system that NREL installed that was more accurate and essentially, what we're using for the basis of determination of meeting that. The Auburn Regional Headquarters was also pretty close, but the instrumentation was using, surface mounted temperature sensors and a BTU meter that had known issues. So I think in general you can say that the performance was almost identical to what the manufacturer had stated. Okay, next slide. So this graph is essentially looking at how the performance compares to both flat plate collectors and evacuated tube collectors. So starting on the left-hand graph, the two black dotted lines are the HSTC collectors that were evaluated. And then the gray lines and blue lines are kind of a random sampling of, standard flat plate collectors that are on the market. And you can see there's kind of an inflection point around 0.4 or 0.04 where over to the right of that, this collector outperforms or has a higher efficiency than the other ones. And so this is essentially, without getting into the equations in the bottom there, this is essentially showing that for applications where the inlet temperature into the solar hot water collector is higher, so like the domestic hot water recirc where the inlet temperature is 110 to 120, this product will outperform all other flat plate collectors. In standard kind of domestic hot water applications, you're going to operate kind of along that curve. And through the simulation modeling, the results are showing that for a standard system, you would have about an 8% improvement in efficiency versus a regular system. You can see the performance also is better than the evacuated tube collectors on the right. We would caveat this with the fact that it's based on gross area of the collector, and so it's a little more difficult to make a comparison to evacuated tubes. But in general, you can see this is a good collector and has higher performance in a number of operating conditions than the other ones. Okay, next slide. So one of the performance objectives was just trying to make sure that the overprotection had worked, overheat protection had worked on the system. And so there's an overprotection device that basically kicks in once the temperature gets up to a certain point. And so during what's called stagnation conditions, where you might have like a hot, clear, sunny day, but it's there's no domestic hot water load, so there's no draw on the system. The panels get into this kind of point where they get very hot, and you have to kind of look and make sure the overprotection devices are working. So for this particular test, you can see that they did work, and around 306 degrees Fahrenheit they kicked in, and everything worked correctly. The one issue, though, was when that happened, the pressure relief valve in the system also activated and dumped a bunch of kind of water and propylene glycol from the system. And so there was kind of a design mistake made in how the system was pressurized. And so I think Alan is going to get into this a little bit more, but it's one of our points here is it's really important that the person installing these is familiar with, the temperatures and operational pressures for solar hot water, which are both typically a lot higher than a standard, boiler-based heating hot water system. Okay, next slide. So this is a graph just kind of showing the energy savings that we realized at the Bean Center. And on the left-hand side, you can see the weekday and weekend 24-hour draw profile. And so there was about 500 gallons per day of water used during the weekday. And the energy savings were about 11,000 kilowatt hours per year. Okay, next slide. So for the Auburn system, you can see the energy savings are lower on this one, but it also had only four collectors instead of 8, and was serving a domestic hot water recirculation loop, which is a fundamentally kind of different design than the other one. Okay, next slide. So one of the main results in the report is, again, looking at where is solar hot water cost effective for the federal government and how does this collector perform relative to other ones. So Greg Barker did a bunch of Transys modeling, and starting on the graph on the right, the energy cost in dollars per kilowatt hour, you can think of that as like the levelized cost of energy. So the red dotted line is like the local utility rate, and any point that those curves are below the red dotted line, it's cost effective. And so we did a bunch of modeling for different domestic hot water loads, different installed costs, different locations, and then different panel types to get an idea of where these systems are cost effective. But rather than kind of giving a single point that says here's what the payback is, Greg generated these curves, which I think are nice because they show that the way the system is designed has a big impact on the economics. So for example, the bottom inflection point of the curve has the lowest life cycle costs. And so if you're just looking for meeting the minimum 30% requirement at the lowest life cycle cost, you would pick that bottom inflection point. If your goals were, maybe a net zero energy building or other goals, you would pick the point that's furthest to the right that has the greatest energy savings but is below the red line. So I think it's just important to note that, using an accurate modeling tool and doing the analysis correctly is important in identifying the most cost-effective system. And there's a lot of graphs in the report that help kind of frame that discussion. And then the graph on the left is showing that the solid lines are the HSTC collectors, and the dotted line is a standard flat plate collector, and you can see there's kind of a slight improvement from the HSTC collector in that it's lower. But for places like Seattle, it's really difficult to get cost-effective solar hot water, and you have to really be at the very bottom range of what an installed cost would be. Okay, next slide. So this is a table that just kind of gives you an idea of what the economics look like for different climate zones. Under the hot water load column, it's modeled with 125 gallons per day and 500 gallons per day. The unit cost ranges from $100 to $46 to $102 per square feet. And essentially, just looking at the hot water load of 125, you can see the economics are not great for every location, which is an indicator that it's important to have a big domestic hot water load that you're offsetting. So even with trying to optimize the economics for that load, you know, they are poor for each location. But for places like Denver and Phoenix, for example, at both the $102 per square foot and $46 per square foot, you know, you have 7.8 to 16.2 year payback and 7.3 to 15. So, you know, showing positive economics there. The point to the right is making that the collector cost is only 20% of the total installed cost. And so if the collectors are, let's say, 20% more expensive, it doesn't make the whole system cost 20% more. It just makes, you know, the 20% for the panels 20% more. So just kind of important to get good costs and make sure you're doing a good life cycle cost assessment. Okay, next slide. So the guidelines for deployment, I think the first one is making sure that all of the loads the system serves are going to stay in place over the lifetime of the system, and then implementing, you know, kitchen water savings ECMs and low flow faucets and things. So I mean, even if you're just serving, let's say, like you know, kitchens and sink faucets, if you put in low flow devices, that can have a very significant impact on the domestic hot water load. So just kind of make sure those are implemented first. We would also recommend installing some sort of temporary metering to make sure you know what the domestic hot water load is and that you're doing that part correctly. The second bullet is just saying it's important to use an accurate hourly design tool to go through those, you know, design considerations that were made. And the third one, which can be tricky, is, you know, making sure you're hiring a trained solar installer. In this case, you know, in some of these cases, the site was under the impression they were using someone who had a lot of experience with these, but there was still kind of design mistakes that were made. And so those considerations of like how many panels to put in series and what flow rate to use through the panels, you know, what PSI setting to set the pressurization to, all of those things are very important and are things that trained solar hot water installers can take care of. And then the last bullet point is just requiring a backup system. Okay, next slide. So for target locations, I think, you know, you do want to target places that have large and consistent hot water loads. The rule of thumb for the report was around 500 gallons per day for weekdays. You know, targeting central hot water systems, although in some cases, especially in places like Hawaii or very hot places, the domestic hot water recirculation loop will be cost effective. You want to make sure that the roof doesn't need to be replaced for 20 or 25 years and that you're not putting the system in a location where the roof needs to be replaced. And then, generally places with high solar resource and high energy costs are going to have the best economics. Okay, next slide. So finally, I think, given the natural gas prices in the United States, it's important to focus on electric backup systems. For some of these that we were looking at, the cost of electricity in terms of like $1 per BTU is as much as 7 times higher than natural gas. So you want to kind of look at, making sure that you have electric backup and, going to have good economics. And then again, using this life cycle cost evaluation method to drive system selection is important. Even with like photovoltaic systems in the federal government, for example, when you're going through procurement on those, you typically, don't require that, a specific PV panel and inverter and racking system is used. You rather use certain metrics, like I want to hit watts per square foot or, lowest life cycle cost. So again, just recommend kind of employing that same strategy, in your deployment recommendations here. Okay, so I think that's all I had, and I think Marty's going to take it over here.
Good morning, everyone. This is Marty Novini. I'm the Energy Program Manager for GSA Region 10. Next slide, please. I personally don't have that much experience with solar hot water design, so as part of this design, we engaged a design build contractor to design and install the system in our building. I have to qualify by saying that our building is fairly old. The piping is very old, dating back to 60s, in some cases dating even older to earlier than that, to 30s. The design build contractor engaged a solar expert into this contract for design and consultation for the most part. And as part of the design, we used to have a cafeteria that was considered, but there were rumblings that the cafeteria is going to close somewhere within, I would say, midway in the design construction process. And of course, after a year after the construction was completed, the cafe closed, which reduced our domestic hot water load by a significant amount. Overall, the system is designed as a, I would say, direct feed into our domestic water loop. And it works very well for us under the present load that we've got. It works better in summer than it does in winter time. We're blessed with a lot of cloudy days. It's fairly mild temperatures in both summer and winter times. So the solar collector essentially works a lot better in summer than it does in winter for us. Next slide, please. This slide shows you the process and instrumentation diagram that was put in place. We have a natural gas boiler existing that essentially exchanges hot water between a tank, about 200-gallon size tank, that also feeds to the domestic hot water loop. The installers put in a dedicated small pump, circulator pump between the collector and the tank, and a dedicated controller that regulates the process for the solar hot water collection. The system only operates when the collector temperature rises above the tank's average temperature by a certain differential temperature. And that is adjustable. I think right now it's set to about 10 degrees differential. Otherwise, it basically does not do anything, just basically sits there. The system, of course, has glycol to prevent freezing. And one other factor is that the solar collector controller is not tied into our building automation system, but the rest of the system, tank temperature, pump operation, and the boiler operation are all regulated by our building automation system. Next slide, please. There are two pictures. These are two pictures of the controller on the right and the small pump that I was mentioning on the left. The system is basically designed and manufactured in Italy, but is also available here very easily in the United States. You can, in the picture on the left, you can see the little pump that I was talking about, and the picture on the right is the controller. Controller is very simple to program. There aren't that many parameters to plug into it. And on the far right, you'll see a controller communication module that you can literally tie into with your laptop to communicate with the controller as well. Next slide, please. This is a picture of the tank that we have in place. Like I said, it's about 200 gallons. On the left, you'll see a cutaway of the tank and what it looks like inside. There's actually two little tanks, one little tank and a larger tank connected to one another, and the collector is connected to the smaller tank on the left that exchanges heated water with a larger tank for storage on the right side. On the picture on the right, you'll see all the temperature sensors that have been installed to measure the stagnation, the stratification of hot water inside the tank. Next slide, please. That was it for me. I'm going to give it to Alan to discuss the beam center installation.
Hello, everyone. Good morning to most of you. It's afternoon for a few of us. I will go over some of the details of the beam center in Indianapolis location for the domestic hot water solar panels. And next slide, please. So as Jesse had indicated previously, we had a very large facility there in Indianapolis, and it's good to note that we actually had a project just prior to this that dealt with the Recovery Act, the ARA projects that were going on, and it actually had to re-roof the whole southern part of the facility there. And so the installation of these panels are actually in that area, and so that goes to some of his points that he was talking about of making sure that that is done so that you have a good payback for everything in the future. We had the 8-panel system to be able to be utilized for a short period of time. But as Jesse had also indicated, we had some issues, and it was found out that there was a failure with the collector loop. It had been filled, and unfortunately, the glycol in the system had boiled and blew a pressure relief valve on that collector loop. And this had actually previously occurred with a similar setup, but these were totally new panels, and unfortunately what we came to find out is that there was some design issues, and we're still going through trying to find out exactly what had happened, but at this time, it looks as though that there was some static pressure on the collector loop that was too low to prevent the boiling at the stagnation temperature. And so that's kind of where we have settled so far with our findings. And so we had a few things that Greg Barker and myself specifically have gone back and forth discussing as to what might be the causes and why the levels were at the points that they were in terms of design. But basically, going back to Jesse's point, the things that we learned off of this was that even though we had an AE that was specifically asked to provide a design for this and working with a manufacturer that had provided these panels, that wasn't enough, nor was it potentially enough to have someone as a contractor who had done work on solar panels before. We came to find out that it was actually more imperative for us to have qualified solar designers on board at the very beginning, and not just an AE that has worked with companies in the past. Same for the general contractor, needing somebody that not just has worked on them in the past, but is more familiar with them and has more expertise and would be able to identify some of those design issues even before we even got into. Next slide, please. So this just gives an idea of some of the things that we would recommend here at the Bean Center was to have a change from 30% to 50% in the amount of antifreeze or the glycol that would be in the system, and then to also increase the pressure from where the designers had it at 15 psi and moving that at a much greater level. Our figures were around 78 psi. So that definitely is in big contrast to what was installed, and as you can see, it is very important to make sure that we have those things correct. Otherwise, we would have a similar situation in your location as with the Bean Center. Next slide, please. Kind of going to what I had just mentioned before, make sure that you have designers that know what they're doing and that have actually seen various reports, including this report that was generated because of this particular assessment, and continue to look at those technologies. They continue to improve, and so that's a great thing for each and every one of you, is that we were able to go through some of the, if you will, growing pains, and we've learned a great amount because of it. Next slide, please. With that, I'm going to leave, and I'll turn it over to Michael Hobson.
Thank you, Alan. Also, thank you, Jesse, Greg, and Marty for your input here. Really interesting presentation on even more interesting technology. So we have some time here for some Q&A. If you've been following along, we have only a few questions here. And if you do have any questions, I invite you to put them in the question bar down there on the bottom right corner of the screen. We also have a representative from the vendor that provided us these Honeycomb solar panels, Zivka Klyer from Tigi, and hopefully you can assist us in some of these more detailed questions that would most likely relate to your product and the performance of your product. So a couple of the questions came up about utility rebates and if they are available for these types of systems, and the short answer is yes. In most cases, there are rebates available. It completely depends on your location. It depends upon your energy provider, local regulations, all of those things. But I believe the best way to answer that question is in most cases, yes, there are rebates, and it helps to reach out to experts that can assist with that, especially with your local energy provider. So there is another question here about air vents. And the question relates to installations in other countries, specifically Germany, where air vents are utilized to help the system cool down. And I don't believe there's air vents on this. And if you could, Zivka, help answer that question. And I'm hoping that you do have availability of your phone. If you hit *6, that should be able to unmute your phone. It doesn't seem like we have a connection right now.
Can you hear me? This is Greg Barker.
Yeah. Hey, Greg.
In case Vika can't get on the phone, I think I can answer the question. The answer is that their design, TG's design, is to use a heat pipe system that's attached to the collector to keep it from overheating. And that's an alternative to using air vents to for keeping them from overheating. So there are no air vents. It's using. Using a heat pipe system. I don't think necessarily. I think it always comes down to what's the payback. So you have to look at how much the collector costs and all that stuff. But in theory, either one should be okay. But the issue is the reason you want to avoid overheating too much is that it degrades the glycol if the glycol gets too hot. So when you have a particularly efficient collector, especially, it's going to get hotter under stagnation. So you have to have some way to keep it from degrading the glycol. And if the air vents are shown to keep it from getting too hot for the glycol, then there's nothing wrong with that. But yeah, after that, it really comes down to a cost question.
Okay. Thanks, Greg. And a couple additional notes, especially regarding the Beam Center installation. With our initial installation, we did replace an existing hot water system that was there. It was a system that wasn't operating, so we took advantage of the existing infrastructure to the best that we could to find value in that installation. We did have an issue with pressure release valve that Alan described. We had the system replaced, but I think from some of the lessons learned during the presentation, really having those knowledgeable installers that have experience with hot water systems is essential here to avoid some of those avoidable incidences that we were experiencing. Let me move on to the next question. First, let me find out if Zivka is available. Do you have audio yet?
Zivka doesn't, but I think there's someone else from TG on the line.
Can you hear me?
Yes, we can.
All right. Thank you very much for the opportunity to talk. My name is Yair. I'm one of TG's engineers, and I can answer several of the questions you mentioned because Zvika is unable to contact us.
No problem. Well, thank you for helping us. Let me start with a question about boiler capacity limitations. There's a question about what the capacity for this would be. And this the definite early answer is it's a project by project determination. But is there a limitation that relates to the capacity?
On our side, it doesn't really matter because the boiler is always on the backup heater. We prefer to do the preheating, and the boiler is, as you said, it depends on the demand, and it depends on probably what there is on site. So on our end, it doesn't really affect us.
Okay. And that's a design determination, something that you would work with the facility. The next question that comes from that is the system manufacturer warranty period. What is the typical warranty for a system like this?
The typical warranty is 7 years on the collectors. And
7 years, okay.
7 years, it includes the whole collector. I mean, if there is any problem, we send in a new collector. Of course, under the warranty conditions that it's pretty much generic.
Yeah, and I think regarding the system warranty, that's something that you would kind of write into your procurement specification. So, for example, if you wanted to have a 5-year system warranty, that could be written in as a requirement for the A&E firm or the installer in that case.
Yeah, of course, system warranty most of the time is given by the installer because of circulation pumps and because of all the pressure relief valves and all that. It really depends on what we do. We learned a lot from this project, and we did several projects since then, much bigger, much more complicated than that. And I can say we learned a lot. And we also do the whole project. We do the installation as we hire subcontractors and we do it by ourselves. And as one of those, we do give all the system warranty. But on this case, of course, we can't give system warranty because we can't take care of the pumps and we can't take care of the pipings and we can't take care of all the installation side of it.
Okay. Let's move on here to another question, and this is an argument I think that we've talked about for a long time. I think we introduced it on this Outbrief, discussing the benefits of hot water, PV with hot water. The question is, why wouldn't we install PV that would that would create electricity that could be used in possibly to sell back to the provider, rather than installing a hot water system? And I think that all relates to the gas cost. But I'll allow you to answer that, Jesse or Greg, if you could give us a little more about that, the debate that we have. Yeah.
Yes. Sorry. Yeah, I can take it. The key component, the key number we can look on it, if we compare it to a PV collectors, is the efficiency. The efficiency with PV collectors will be somewhere around 15 to 18, maybe 20 those days. And when we're talking about the hot water collectors, we're talking about efficiency that can rise up to 80 or 82%, as you show in the graphs just on the PowerPoint you showed. So the question is, what we use it for? If you need only electricity and there is no hot water consumption in the building, it will be smarter to have PV. But unless you have hot water consumption in the building, as you describe the cafe or as you describe employees' showers, it will be much wiser to use the higher efficiency you can achieve. Of course, you prefer to use 80% of the sun instead of 15%. And in the end, energy is energy. Kilowatt hour is kilowatt hour. And it doesn't matter if it's a kilowatt hour by heat or by electricity. And that's the key number we should look on, the efficiency of the collectors. And PV collectors, because of the technology, PV collectors are much less efficient than hot water collectors.
Well, this is Greg Barker. I have to sort of disagree with that being the bottom line that you should look at. I think what GSA is supposed to do is look at what is most cost effective. And if you can buy a less efficient thing for a lot less money, then that still may be more cost effective. So I don't know the actual numbers, but I think it's a fair question to say what is more cost effective to deliver the energy I need for heating my hot water? Is it using photovoltaics or is it using a solar thermal system? And that should be, in my opinion, that should be the bottom line to look at. And not how efficient the collector is, because that doesn't say anything about the cost.
Yeah.
Thank you, Mr. Barker. I agree. I agree with everything you said. I have nothing to say, but I agree. And if we look on the engineering point of view, let's say I took the engineering point of view. Like you, I don't know to say the numbers. I don't know to say the exact numbers of the ROI, the return of investment, and stuff like that in the state. But if you're talking on the engineering point of view, the efficiency is the key number.
Right, but I think for these building managers, what they want to know is how cost effective is whatever measure I'm going to do be. And so that's why in our whole report, we made a point of giving you some graphs that if you talk to a solar installer and contractor and say, how much will it cost me to buy these collectors and have this system installed, then you can look on the graphs and get an idea of what the payback is. And likewise, you could do the same thing and go to a photovoltaic installer and ask them, how much will this cost, and do the same math. And I think that would be the way to make the decision between the two.
Isn't it also important to make sure that we're looking at the usage of the hot water in the building? Because we're not just looking at efficiency of the collectors and comparing the two, but you're also making sure I'm going to use all this water. Because if you don't use all that water, that comparison of efficiency, it doesn't really matter.
Right, and that's part of the of all the graphs and the end of the report are assuming different hot water loads. Here's what the payback would be. So you're right. You need to know what your hot water load is, load being gallons per day or something like that.
That's true. As long as you have, as higher as the consumption will be, the efficient the system will be. That's pretty clear because you already have the tanks and the pipings and everything. So adding more collectors or enlarge the tanks will be much cheaper than establishing a new system. So as long as the consumer is bigger, it's much more economical and it make much more sense to go for those systems.
Yeah, and I think that's what we had in the report was it was clear that larger hot water loads made it more cost effective, which is what you're saying.
I agree. Since then I think we installed around I think 2,000 square meters of collectors with projects of around 300 square meters of collectors each. So we did use pretty big arrays of collectors for pretty big hot water consumption. So as I said in the beginning, we did learn a lot from our journey together.
Yes, that's true. There's a lot of lessons learned on these installations, and overall, a very good experience. I see we're running out of time here. I just want to add one more thing from our Q&A. And if your question wasn't answered, we'll definitely get back to you. I don't think we have all the answers here, but one of the statements that was provided here is about system operation temperature and pressure, and some of the questions about finding informed contractors that understand how these systems work. One of the points made is not using PVC piping. That would degrade, of course, with some of these high temperatures, and definitely something you don't want to go forward with if that is part of the plan. And if there's any other questions, we would love to hear that, and we would love for you to provide those to us. We can, as we do in the past, respond with some of the other questions and answers and sort of a full review of what we've discussed. I guess with that said, Andrea, I'll hand this back to you to close it out.
Great. Thanks, everyone. Thanks for attending today's webinar. And as mentioned, if you'd like to receive a continuing education credit through the American Institute of Architects, complete the post-webinar email survey. And if you don't receive that survey, please contact Michael Hobson. Thanks, Michael. Thanks for all the presenters, and we look forward to seeing you all on next month's webinar.